Thanks Shouting for the very kind introduction, and thanks the EASF committee for the invitation and a great organization. So today it is my great pleasure to share with you some of the works I have done during my PhD period at MIT with Professor Jeremiah Johnson. So my PhD study has been primarily focused on an important yet often overlooked aspect of polymer networks, which is their topological structure. So as Shouting mentioned, my experience and background is heavily on chemistry. So we're really trying to understand existing materials from a molecular perspective and trying to create new materials from a synthetic standpoint. So I'm really excited for this opportunity to present my works to this particular audience that focus more on applied science. So hopefully my chemist approach and your engineer vision can together stimulate some new ideas and new thoughts. So polymer networks are network structure made of polymers. So they are essentially everywhere in our daily life. So for example, rubber bands, rubber tires, and many hydrogel-based cosmetics, they are polymer networks of different forms. And just as you can see from these pictures, this class of materials really have a lot of unique properties that distinguish themselves from other types of materials, including their elasticity, solvent welding ability, and tunable mechanical properties. So if you think about the structure of network-based materials, what you have in your mind is probably like this. So for example, in this particular solid-state material, which we chemists term as metal-organic frameworks, the nodes are perfectly aligned in this space to form a long-range order. And therefore, this material is crystalline, rigid, yet brittle. However, the majority of polymer networks, including those you will find in everyday products, are amorphous, which means they lack long-range order, are abundant in topological defects. So if we take a real polymer network, which is composed of those nodes that are connected through polymer chains, and we call those nodes as cross-linking junctions, and you may find its topological structure even more complicated than you thought, and including several important topological features across really different length scales. So at large length scale, typically above 100 nanometer, we are mostly dealing with inhomogeneous distribution of those cross-linking junctions. And as we go down to 10 nanometer, we are reaching molecular level topology, and we will find features such as cyclic defects. The most abundant one, of course, being those primary loops, which are formed due to intramolecular reaction during those cross-linking steps. And as then we have secondary loops, which means two network junctions are connected through two chains instead of just one. And of course, we will have some high order cyclic defects such as ternary loops. And we will also have dangling chains where only one of its chains is connected to the polymer network. And the last but not the least, we have a very important topological parameter, branch functionality, which describes how many polymer chains are connected to the junction. So throughout the years, many efforts have been made trying to understand and characterize these topological features. And these studies have really demonstrated that perhaps any of the parameters I mentioned here plays a very critical role in dictating the material properties. So if topology is such an important parameter for polymer networks, a question we naturally want to answer is, can we develop strategies to control these topological features, therefore control material properties from bottom up? So part of my PhD is focused on trying to solve this challenge. So I have developed several general strategies that enable us to control different aspects of those polymer network topological features. And following these works, I have gone even further to downstream, of course, downstream to our chemists, essentially leveraging network topology as central design principle to create novel or functional materials. So for the sake of time, today I will only introduce one work from each of these two aspects, hopefully to give you a flavor of how we tackle this grand challenge of controlling polymer network topology. So let's start with something simple, primary loops. So a typical way to make polymer networks is mixing a bifunctional monomer A2 together with a functional stop polymer BF. So if the A group reacts with B group, we will get a crossing polymer network where the junction now is connected to another junction through those polymer bridge. And this molecular connectivity really contributes to the elasticity of the network-based materials. However, if the same A2 reacts twice with the same BF, then we would get a primary loop junction. So because primary loops do not contribute to the connectivity of the network. They are elastically defective. So which means when you stretch a polymer network, things simply can't be stretched. Therefore, a lot of elastic energy is essentially wasted in those primary loops. So in order to correctly understand these primary loop features, a natural question you may want to ask is how to quantify those features, right? So before our group got into this field, it was generally considered to be impossible to analyze these features either chemically or spectroscopically. So luckily in 2011, our group developed a very simple strategy, which I will introduce several slides later. And this strategy really enables us to precisely quantify primary loop fraction in model polymer networks. So using such strategy, we systematically examine how these primary loops affect the mechanical properties of polymer networks. So we synthesize two polymer networks where we know exactly the primary loop fraction in them. Then we use shear rheology to measure their storage modulus. For example, for this particular synthesized polymer network on the left, its storage modulus is a little bit below 20 kilopascal. On the other hand, because we know the concentration of this network as well as the molecular weight of this network strands, we can use some elasticity theory to predict the storage modulus if we assume there's no primary loop at all. And this theoretical prediction gives really a storage modulus much higher than the experimental measurement. So obviously, this large discrepancy between experimental data and theoretical prediction is due to the presence of these primary loops. So indeed, our method shows that there are about 25% polymer chains in this network that are primary loops. And if we take this primary loop into account and modify our theory a little bit, we can get a new theoretical value that is now pretty close to the experimental data. So very obviously, those loop defects weaken the polymer network dramatically. So if those loops are so detrimental, you may want to ask a second question. Can we then develop a general strategy that controls those loop fractions in order to enhance the mechanical properties of the materials? So after carefully considering the process that form the primary loops during the network formation, we propose to use semi-batch monomer addition to achieve this goal. So instead of directly mixing A2 and BF monomer together, we propose to use a syringe pump to slowly add BF precursor to A2 monomer. And we argue that this is going to give us a loop-depleted polymer network. So here's our rationale. In the beginning of the addition, we have a pool of A2. As we slowly add B4 to the system, and as long as the rate of addition is much lower than the rate of reaction, we would get lots of A4-like species, which are star polymers with chain ends capped with A2, right? And as we keep adding B4, because A is still always in excess, we would get lots of hyperbranch polymers with chain ends again capped with A. So if you take a closer look at those hyperbranch polymer structures, you may realize that because A can't react with A, so it has to react with another B4. Therefore, there's no way to form primary loops from those structures. So therefore, if we keep adding the rest of B4 quickly to reach one-to-one stoichiometry, we would, in principle, get a loop-depleted polymer network with enhanced mechanical properties. So to demonstrate our hypothesis in a real polymer network, we synthesized a model network where we can measure primary loop fraction using strategies I mentioned earlier. So the structure might look complicated, but I just want to point out two things here. So first, we are using azide and alkyne stream-promoted azide-alkyne cycle addition to form the network because this reaction is very clean and very efficient, doesn't require any catalyst. And second, very importantly, we install a degradable ester bond. So second, in order to quantify the primary loop fraction, we synthesize two types of B4. So one having 8 hydrogen atoms between a terminal azide and a installed ester bonds, while the other having 8 deuterium in the same position between the azide and the ester bond. So after we form the network, we can use either base or light to cleave this ester bond. And therefore, this isotopic label will now cross over from B4 to A2, essentially generating 3 degradation species, NN, NI, and II. So which differs in the distribution of those isotopic labels. So because the formation of loops is intramolecular, so the loop size can only yield NN or II. while an ideal junction can yield all of these three possibilities. So therefore, after we use LCMS to quantify the distribution of these three degradation species, we can use a very simple mathematical equation to calculate the primary loop fraction. So here is just a representative result. As we increase the concentration, the primary loop fraction decreases. So this is simply because at higher concentration, it favors interjunction reaction while suppresses intramolecular reaction. So and our experimental data is consistent with rate theory simulation we performed. So with this system in hand, we went on to test our strategy. So first in a low concentration. So at this particular concentration, if we directly mixing A2 and B4 together, we are only going to get a soluble hyperbranch polymer solution because of the abundance of these primary loops, which prevent the percolation in the system. However, after we use a syringe pump to slowly add B4 to A2, and as the rate of addition gradually decreases, we see the loop fraction in the film network also decreases until it reaches a plateau where the loop fraction is now only half of that in the batch mixing counterparts. So more interestingly, we found that the reduction in primary loops enable us to form a freestanding gel in a concentration that is essentially below this regular gel point. So encouraged by this result, we tested our method in a higher concentration. Again, we see the semi-batch monomer addition greatly enhanced the storage modulus of the gel compared to the batch mixing counterpart. And we then confirmed that this increase in storage modulus is indeed a result of reduction in primary loop fraction. So we then tested our method in really a series of polymer networks with different branch functionalities and different gelation chemistry. And to our delight, our method seems to be a very general method that enhances mechanical properties of all the model networks we have tested so far. So among them, I just want to talk about a very special case, which is this famous Tetrapep gel that is made from essentially A4 plus B4 precursors. So again, semi-batch monomer addition enable us to form a freestanding gel in a concentration which is below the regular gel point. And at higher concentration, semi-batch monomer addition enhanced the storage modulus of the material by almost 2-folds. So nothing looks too special so far, right? It's just the same as we observed in the previous slide. However, if you take a closer look at those precursor structure, you may realize that because A can't react with A and B can't react with B, so one A4 precursor has to be connected to another B4 precursor. So Tetrapep gel is essentially primary loop free. However, it still contains some higher order cycle defects, so such as secondary loops, which also plays a negative role in the material properties. So given the observation we had here that semi-batch monomer addition still enhanced the mechanical properties in the Tetrapep gels, we wondered maybe our strategy controls secondary loops as well. This was purely a hypothesis back to the time when we published this paper. So later on, we had a postdoc in our lab who developed a strategy enabling us to simultaneously quantify both primary loops and secondary loops in model polymer networks. So using his system, we confirmed that semi-batch monomer addition method not only decreased primary loop fraction, as we see earlier, but also decreased secondary loop fraction. So really, semi-batch monomer addition is a very powerful tool enabling us to control cycle defects of various orders in polymer networks. So I think this strategy not only shows that we have the ability to control polymer network topology, but also provides a very good example demonstrating that topology plays a critical role in dictating material properties. So if topology is such an important parameter for polymer networks, a route that we naturally follow here is using topology to create some functional materials. So more specifically, we ask ourselves a question: can we develop a type of material where we can have it switch between two topological states? So because topology is a global parameter, we would expect a variety of properties will switch simultaneously as we switch topology. So from many microscopic features to macroscopic, including their static, such as modulus, and dynamic, such as stress relaxation ability properties. So really, the ability to switch network topology can enable us to switch multiple aspects of material properties simultaneously in a really coherent fashion. The problem is how to achieve such a system. So as you would expect, this is extremely difficult to achieve in a traditional polymer network, where these cross-linking points, we just assume them as very simple point connections. So in order to achieve our goal, we need some basically smart cross-linking points that can reorganize their structure upon certain regulation, right? So in other words, a high degree of structural complexity needs to be programmed into these junctions. So while it took me a while to figure out what's the best way to increase structural complexity of these network junctions, it turned out that the solution I was looking for was actually in type of material our group developed earlier, which is polymer metal organic cage gels, polymer gels for short. This class of material was really inspired by the work from Makoto Fujita's group in the University of Tokyo. So in 2004, the Fujita group reported upon mixing this very simple bis-pyridine-based ligand together with palladium-2+ in solution. Then spontaneously, they would form some complicated yet well-defined metal organic cages. So in this case, each cage now contains 12 palladium atoms and 24 organic ligands, where this palladium atom is connected to another palladium atom through this ligand via the formation of palladium-nitrogen bonds. So following this result, later on it was found that just by simply changing the bite angle between these two pyridine coordination sites, a variety of metal organic cages can form, ranging from M2L4 all the way to M48L96. So inspired by these results, a former graduate student of our group proposed to incorporate such ligands into two ends of polymer chains. So upon mixing this polymer ligand with palladium-2+, he successfully constructed a network where the junctions are these seemingly very complicated metal organic cages, right? So the polymer chains are now connected by these cages. If we assume there are no cyclic defects, of course there will be a lot in reality. The theoretical branch functionality will be 24. So this very high branch functionality leads to a variety of unique properties for polymer gels compared to traditional polymer networks. So with this idea in mind, the solution to switch network topology becomes simple, as long as we have some smart junctions or smart cages that can switch between small cage and large cage. Then upon incorporating such cage as network junctions, we can simply switch network topology by switching this cage topology. So likely this type of cage does exist. So inspired by the research from the field of stimuli-responsive metal organic cages, we developed and synthesized a polymer ligand that incorporates two photoresponsive ligands. So in these photoresponsive ligands, the bite angle between these two pyridine coordination sites can be drastically changed upon UV or green light regulation through the reversible ring closing and the ring opening reaction of this diarrhyl ethane moiety. So in this small bite angle state, it forms a small cage with palladium-2+ in the form of palladium-3L6, while in the large bite angle state forms a much larger cage with palladium-2+ in the form of palladium-24L48. First of all, using some small molecule as model compound, we confirm that this switching between small cage and large cage is quite robust in solution state. So we then went on to mix our polymer ligand with palladium-2+ in solution. Immediately, we get a freestanding gel, and shear reality shows its storage modulus much higher than loss modulus, so indicating it's very elastic. And as we shine UV light on the material, we found the material changes color, but still behave pretty elastically. So however, if we take a closer look at the storage modulus value of this material, we found UV light actually increased storage modulus by almost 2-folds. So moreover, green light can reverse this process. So in order to confirm that this switching in the mechanical properties is indeed a result of topology switching, we perform a small angle X-ray scattering on the material to probe its topological structure. So just as you can see here, for the gel before UV irradiation, the Sachs curve is almost featureless, right? So with the broad peak here indicating its cross-linking materials. However, as we shine UV light on the material, we see this broad peak gradually shifts to low Q and becomes sharper. And moreover, we see a bunch of new peaks showing up in high Q region. So what does this really tell us? So well, for the gel before UV irradiation, we attribute this broad peak to the junction-to-junction distance. which gives a d-spacing about 7 nanometer. So this is consistent with the size of polymer chains we use, plus the diameter of the palladium-3 F6 cage. So if we zoom in the high Q region of this profile, we can actually find a small PQ, which is attributed to the form factor of a palladium-3 L6 cage, indicating the presence of nanoparticle-like structure with radius about 0.8 nanometer. So after UV radiation, we found the junction-to-junction distance increased to 12 nanometer as we switch the small cage to large cage, therefore increasing the junction-to-junction distance. Moreover, the 5 peaks in the high Q regions, we can attribute them to the form factor of palladium-24L48, which gives a radius about 3 nanometer. So really, SAX provides quite convincing evidence for the topology switching in our material. So besides of the static properties of the material, such as the modulus, we wondered, do we also change its dynamic properties upon switching topology? So very simple rationale is, for this type of small cage, it's well known that they have very fast ligand exchange rate in the solution, with half-life much shorter than 3 hours. However, for the large cage, because of the cooperative effect, it has a very slow exchange rate with half-life longer than 20 days. So because the network dynamics is a macroscopic reflection of the ligand exchange rate in the macroscopic, so it seems reasonable to assume that switching topology also switch the network dynamics. So in order to probe that, we performed a stress relaxation study to obtain some characteristic relaxation time, tau. Tau is simply a sign of how fast a material can relax stress. So for both the gel before and after UV radiation, we found as we increase temperature, the tau value gradually decreases. So this is simply because of the accelerated ligand exchange rate at higher temperature. However, at the same temperature, the tau value for the gel before UV radiation is always 1/4 of magnitude longer than the gel before UV radiation. So in other words, upon switching topology, we can essentially switch the material from a highly dynamic state to a low dynamic state. So this potentially enables us to achieve some interesting conditional self-healing properties of the material. So for the gel before UV radiation, because of the very fast network dynamics, it is self-healable at 40 degrees. However, if we use UV light to switch topology, the material becomes non-self-healable. Moreover, if we use green light now to switch topology back, we find the material regain its ability to self-heal itself. I have to mention that this type of conditional self-healing is very difficult to achieve in traditional polymer networks. And our topology solution provides a great way to break this limitation. So hopefully with the works I talk about today, you can agree with me that controlling network topology is not only necessary in order to understand polymer network properties, but more importantly, provides a unique way to create new functional materials. So this is really the message. I wish you could take that if I didn't make my points clear. So with that, I'd like to thank my advisor and all the collaborators I had in MIT and outside MIT to help me accomplish the works I just talked about. And I want to thank again EASF for the great organization and invitation. And thank you so much for your attention. And I'd be happy to take any question if there's any.
Thank you very much, Yuwei. This is a very interesting and excellent talk. Maybe Xiaoting, you can ask your question.
Yeah, let me start asking maybe 1 or 2 questions. It's a very nice talk, and it's super fundamental and also of great interest. The first question I have in my mind is you're talking about the several actually critical topological defects in polymer networks. You mainly actually talk about the primary groups and the secondary groups. My question is for the first 2 material systems, one is the A2 plus B4, the other is the A4 plus B4. How are the dangling chains present in these 2 material systems? And how these, basically how to quantify dangling chains?
That's a good question. So dangling chain. So dangling dangling chain is something that will form if you have either incomplete reaction between A plus 2, or you have a basically off stoichiometry between A and 2 groups, right? And in my system, either for the A2 plus B4 or the A4 plus B4, first of all, I use very efficient and clean reaction. And second, I always try to balance the stoichiometry to when to work, at least try my best. And so I try to quantify this dangling chains with NMR and IR. So IR can tell you the unreacted functional groups in the material, but not very quantitatively. But NMR can tell you the relative unreacted percentage of these functional groups more quantitatively, but would be very difficult to perform on a solid state material. So what I found is, in general, the reaction efficiency is above 95%. So I don't see lots of dangling chain in the system. So I just assume there is a negligible amount of dangling chains. But you are right, dangling chains is very important, especially when you have off stoichiometry or incomplete reaction. In that case, I believe NMR and IR can give you at least a semi-quantitative measurement of these dangling chains.
Okay, great. Thank you so much. Thank you for detailed explanation. So I have one more question, but I would like to leave this opportunity to all attendees. Chuang Li, if you can speak, you can just ask your question in person.
Okay, thank you. Hi, Yuwei. Nice talk.
Hi.
So I have a question about your Nature paper talking about the small cage to the big cage change. So after you shine the UV or green light, so you measure the property, mechanical property change. One thing, have you ever observed any volume change of your gel after the irradiation?
That's a great question. This actually has something to do with how we perform this experiment. So I don't want to mislead you that this transformation between this small cage and large cage is immediate and transient. Actually, we have to heat the system at usually 45 degrees with UV light or green light for about 4 hours. So in that case, all the potential strain or work in the system will be relaxed, right? So therefore, I don't observe a very obvious volume change because, again, the strain are relaxed completely with this heating process. But I've actually also done this experiment at room temperature with a UV or green light, very short time irradiation. And I do observe some volume change. So as the gel switched from small cage to large cage, the volume actually increased a bit, but I didn't measure that quantitatively.
Okay, great, thank you.
Yeah.
Hi, Jing. Do we still have time for one more question, or we?
Yeah, maybe we can ask one more question.
Okay,
and we can
let me just answer one more question. Anyway, that may not be very directly to your work, but I just may consult you one question about the rheology data you have presented. So for the G prime and the G double prime, so my experience, let's say two material systems. One is polymer started from macromer. Let's say Tetra and PG you have made, or many of the material your groups have made. Or the other system is actually started from polymerization from monomer, something like a polyacrylate. So what I have found is for the first system, the G prime basically is rate independent, so it's just like what you have presented here. But for polyacrylate, what I found is show a pretty actually significant rate dependency. I just want to see, do you have any such kind of understanding making such kind of difference? Or is it something like just due to entanglement? This is my current understanding, if that is true or not.
So by saying rate dependent, you mean like the rate is the rate you perform this rheological measurement, right?
So basically, is the modulus is increased with this omega frequency.
I see. Yeah. So the G, mostly the G prime, right?
Yes, G prime. Let's just focus on G prime.
Okay. That's also a great question actually. So I will go back to this.
Yeah, my current understanding, because if let's say polymerize from a polymer system, I feel the chain-chain interaction seems like to be mostly can be prevented, something like that.
So I believe I actually would agree with you that the effect is from mostly from entanglement, but also there are another I think a second reason. So first of all, entanglement for this, for example, Tetrapep gels, right? You make from macromer. Actually, you are not using a very large molecular weight polymer precursor anyway, right? So it's like usually 5K. It's actually not too higher in terms of the entanglement compared to the entanglement molecular weight of PEP. So we always assume there's a negligible entanglement in the system. Sure. While for the gels you say made from polyacrylamide, actually those gels, the molecular weight of each polymer strand is very high. So there is very good chance for the polymer chains to entangle.
I see.
So entanglement will result the phenomenon you observed. But also I think there's a second reason. So for those gels you made from chain growth approach, right? Mostly from polyacrylamide or other type of monomers or polymers. Those gels, because they are made from a radical reaction, and those reactions are usually very fast. If you think about the mechanism, so you have to locally generate a radical, and that radical is very short-lived. So it propagates very rapidly around that radical and terminates very fast. So what the result is a inhomogeneous distribution of those cross-linking density in the system. So so in that case, you have basically locally different distribution of these junctions. Some parts of the gel is is densely cross-linked, and some part of the gel is loosely cross-linked. That in my experience will result in basically I think very bad reproducibility in terms of measurement.
I see. Yeah, that's true.
Yeah, so I think two reasons. The first is entanglement. Second is this inhomogeneous distribution of cross-linking density. So actually, I discussed the mechanism of that chain growth polymer network in this Angvanta review. So if you are interested, you can take a look.
Sure. Great. Thank you so much. Due to the time, let's move on to the second speaker. And I also noticed one more questions. Probably we can just leave the discussion after all the speakers for control the time. Okay. Thank you, Yuwei again. Thank you.
Thanks everyone. Yeah.